In this lecture, we're going to analyze the periodic table and see what order it has. And then we're also going to see how the electronic structure is represented in the order that the periodic table has. The periodic table is arranged in rows and in columns. The rows are called periods, and the columns are called families or groups. This is the first period, this is the second period, etc. This column here is a group or a family. You will see that it has on the periodic table a number labeling the top of it. This is called 1A in your book, and this is called 2A, 3B, 4B, and this one is 3A and 4A. Those numbers are rather arbitrary, and they vary from book to book and issuing of the periodic table, and so they're not quite as useful to use. However, all periodic tables separate the elements into areas in the same manner. If you draw a line from boron down to astatine, this line is the metalloid line. All the elements that are on this line are considered to be metalloids. Metalloids have properties that are halfway between those of nonmetals and metals. The nonmetals are to the right of the periodic table. They tend to be poor conductors, dull. Most of them are even gases: helium, argon, krypton, fluorine, chlorine, oxygen, nitrogen. They're all gases, aren't they? But they tend to be non-conductors, good insulators, and dull if they are solid at room temperature. To the left of the line, you have the metals, and those all tend to be conductors, shiny, good electrical conductors, good thermal conductors also. The periodic table have regions that have names. The first family in the periodic table, right here, this first column, is called the alkali metals. They all have properties that are similar to each other, as do all the other groups. The alkaline earth metals are right here, and they have properties that are similar to each other. The last column on the right, the noble gases, they're also called the inert gases. And then to the left of them, you have the halogens. The representative elements are those elements that are in the first two columns and the last six columns. We have the transition metals in between the two groups of representative elements. The representative elements have simpler, more straightforward chemistry. The chemistry of the transition metals can be more complicated. The periodic table has another place that is down below the periodic table, and it is called the rare earth elements or the intertransition elements. And if you look at the numbers, the atomic numbers, you're going to see that they fit right in here after lanthanum and actinium. As a result, this row in the intertransition elements is called the lanthanide series because it comes after lanthanum. And this row is called the actinide series because it comes after actinium. Electronic structure is very organized. Electrons cannot be just anywhere outside the nucleus in a random cloud. They have very specific places where they fit and only certain energy levels. And that's what we're going to investigate in the next few slides, actually next several slides. Now, the places where these electrons can be is almost like an address. The first part of the address is called the principal energy level. That principal energy level are given symbols, n equal 1, 2, 3, 4, 5, out to infinity. Within each principal energy level, you have sublevels, and the sublevels can be S, P, D, F, and G, H, I, on out to infinity also, but the ones that we see in atoms are S, P, D, and F. That's where ground level or ground state electrons are found. Within a sublevel, you have orbitals. An S sublevel has only one orbital. A P sublevel has 3 orbitals. A D sublevel has 5 orbitals, and an F has 7 orbitals, and on and on. G would have 9 orbitals if we saw ground state electrons in G. Within an orbital, the electron can either have its spin up or down. And this basically describes where you can find electrons. An electron can have a principal energy level, let's say n equal 2, sublevel P, orbital number 2, and spin up. Or it can be n equal 2, sublevel P, second orbital, spin down. You can see because spin can only be up or down, within one orbital, you can only have 2 electrons. Now, I'm using the word level. Your book uses the word shell instead. That's an older term. I tend to use a more modern level term. The energy of the electron will change as it goes from place to place on an atom. Principal energy levels indicate how far an electron is from the nucleus. If the n number is high, an electron is far from the nucleus. If the n number is low, the lowest is n equal 1, well then the energy is very low. So if an electron is in the n equal 1, it's closer to the nucleus and low in energy. If an electron is in n equal 3, it's farther from the nucleus than the n equal 1 electron, and the energy of that electron is higher than that of n equal 1. The sublevels go from S, P, D, F, those in that order. The lowest energy is S, the highest energy is F. In a sublevel, all the orbitals have the same energy. We say their energy is degenerate, meaning all the same. If I look at a 5p, n equal 5, p sublevel, I'll find 3 orbitals, and each one of those orbitals has the same energy. Spin up or down has the same energy. The 2 electrons in one orbital their energy will be the same whether up or down. It's just they have to have opposite spin if they're in the same orbital, because no 2 electrons can be in the same place. They have to have separate places, and spin up or spin down are separate places. The places that the electrons can be defined as a specific volume around the nucleus. This shape where the electron resides is basically where the electron can be thought of as moving in that little volume. Each type orbital has a specific shape. S orbitals have a spherical shape. P orbitals have dumbbell-like shapes. The S sublevel has only one orbital, and so the orbital within that sublevel is spherical. But the P sublevels have 3 different orbitals. Each orbital has the same dumbbell shape, but they're oriented at 90 degrees to each other, so they're in separate volumes. Because when you go from n equal 1s to n equal 2s, you're getting farther from the nucleus. The sphere of 1s is small and close to the nucleus, and the sphere of 2s is farther away from the nucleus. If I compare the shape of 2s versus 2p, 2s is spherical, 2p is going to be the three dumbbell shapes. Remember, there's three orbitals, one orbital, two orbitals, and three orbitals in a 2p sublevel.
In describing the places of where an electron be, or the location of electrons, we always have to remember that electrons are trying to get as close as possible to the positive charge of the nucleus. They're negatively charged, and that positive charge attracts them. So they always get as close to the nucleus as possible, which is the lowest energy place. If I want to write down where the electrons are, I use this thing called electronic structure, which I'm showing you a blank electronic structure here. The lowest possible energy place is the 1s sublevel, and it has only one orbital. The next highest would be 2s with one orbital, and then 2p with three orbitals. Then on top of that you would have 3s, and there's more, but what we're going to do is look at what an atom with 8 electrons would look like. Where would those electrons be? So the first electron would have to go into the lowest possible energy place, 1s. Next, the next electron coming in wants to get as close to the nucleus as possible. Now, it does not like getting close to an electron, but it does want to get as close to the nucleus as possible. So to do that, it will get into that 1s sublevel with an opposite spin. There is a place 2 electrons can be in any one orbital. They just have to have opposite spin. We indicate either spin up or spin down with an arrow in one of these boxes. So now in that 1s sublevel, you have 2 electrons occupying it. Next, an electron would go to the next highest energy level, which is 2s, and it can have another electron with it. So now there's 4 electrons shown on this atom, and those would be the places where the 4 would be. The 5th electron cannot fit into a 2s sublevel because it has only one orbital, and one orbital can hold only 2 electrons. So it would have to go into the 2p sublevel. Then the 6th electron would go into the 2p sublevel also. Now I'm showing it going into a separate orbital. That's because electrons try to get as far away from each other as they possibly can without getting farther from the nucleus. And then the 7th electron would go into the last 2p sublevel. Now what would happen is an electron, the final electron in this atom with 8 electrons, would go into a 2p orbital with another one with an opposite spin. It wouldn't matter which one. We just usually tend to write them in order.